Well, thanks, Scott, and for inviting us to, the PCEA, for inviting us to talk today. So, again, probably a lot of you are probably not familiar with the name Quantic. You're probably familiar more with our, the actual company, which is Ohmega and Ticer. So first, I'd like to ask, how many people have actually designed with embedded resistors before? Anybody? Oh, okay, there's a few. So anyway, so I'd like to cover our novel thin film resistor material. But first I'd like to talk a little bit about Quantic, because again, this is a relatively recent development. So Quantic was formed by, there's an investment firm called Arcline, is buying up companies that specialize in military, high rel, and some commercial aspects, and putting them all together into this Quantic group. So let's give you a quick overview of our parent company. Global leader in aerospace, defense, and commercial markets. We have over 15,000 products with 1,500 customers worldwide, about 800 employees in 20 locations. Except for 2 locations, are all pretty much in the U.S., dotted along the East Coast and the West Coast, and a few in the middle. And we have, when you add up all the companies, we have over 60 plus years of history serving mission critical electronics, and we have strong patent and IP position. So, we have quite a few companies under the Quantic umbrella, but they basically go into 3 major groups. We have RF and microwave products, sensing products, and power products. And the Ohmega and Ticer products fall under the power products. This is just a kind of a quick overview of some of the things that we do. So, again, RF, sensing, and power products. So, oscillators, encoders, accelerometers, high power capacitors, resistive foils, which is what we do, magnetics, power dividers, filters, converters, all these type of good things. And then we also are in a lot of programs like the Joint Strike Fighter, Air and Missile Defense Radar. If you own an iPhone, our products are in it. And key components of medical equipment from Abbott, GE, and again, over 60 years of space pedigree, working with NASA and others. And again, we serve a pretty broad market, but a lot of it is in the high rel and high, mission critical type products. And we're mostly a tier 3 and tier 4 supplier, so we don't make, integrated systems. We basically make the components, and in our case, we actually make materials that go into components. So, but we work very closely with the, the tier 3, tier 2, and people to meet the requirements. So getting on to the reason why I'm here today, again, I've had 40 plus years in the printed circuit board industry, working at board shops as well as in the materials. I spent a lot of time at Oak Mitsui, where we make copper foil, and when we developed the Farifix line of product, which John will talk about in a little bit. And it turns out that when I was working at Oak Mitsui, we were supplying the copper to Ohmega and Ticer. So I have a long history of working with this company, even though I've only been on board for 2 months, officially working for them. So again, the technology for, there's two things I want to talk about. One is the Ohmega, which is a nickel phosphorus that's plated on copper foil, and the other one is the Ticer product, which is a nichrome that's actually sputtered on copper. But the actual technology for Ohmega goes back to the 1970s. Okay, it was developed by a company. Some of you are old enough. I think I see enough old people in the room that can remember Micah. Yeah. So anyway, but the technology was then, and then it was taken over by Gould, and then remember people Gould foil, and then over the years, then Ticer, Ohmega was actually by itself, and then Ticer was taken over by Gould, and then they became their own company. So Ohmega's been around for a long time, and then 2 years ago, it was bought out by the Quantic group. The Alan who started the company, who's 95 years old, and said, I think it's time to get out of the business, so he sold it to Quantic. And then a little bit of time after that, Quantic acquired the Ticer assets. So now we have both product lines. So again, it's just a quick timeline. Again, the Gould product is probably a little bit younger. It only goes back to the early 2000s. But again, it has a long pedigree of being used in critical applications. So when you think about it, we're starting out with a basic resistive blank slate. We're taking copper foil, and then we're going ahead and we're putting a resistive layer across the entire copper foil. So in the case of Ohmega, like I said, we have a plating line, so we plate nickel phosphorus onto the copper foil. In the case of the Ticer material, we actually do we have a huge sputtering chamber. So it's a reel-to-reel process. We draw vacuum, and then the copper goes through the sputtering targets, and we apply the nichrome or a few other elements to make the difference. So we make a nickel, chrome, aluminosilicate, and also we have a chrome silicate. So we have, again, different resistivity levels. So we can plate 3 different materials. We can sputter 3 different materials for different resistivity levels. For the Ohmega, we basically control the resistance by how much thickness we put on. So the thicker the layer gets, the lower the resistance. But again, it's the entire sheet, so you're doing a subtractive process. So common uses, we have a range of resistive, and I'll get into what it's an interesting concept. It's ohms per square is how we define it. And so we go from anywhere from 10 ohms per square up to 1,000 ohms per square. And then I'll get a little bit into why you would pick each one. But typically the 10 ohm material is for like termination resistors. You can actually put a resistor in trace, and I'll show you an example. But also people are looking at now heaters now. It's a good material for embedded heater circuits. And then the 25, 40, and 50 ohm are probably the largest usage. And those are used for series and parallel termination resistors, filters, RF and microwave power dividers. But then we get into some higher ohmic values. They can use like, without 100 ohm as primary pull down and pull up resistors for digital logic circuits. And then you can start getting some really high ohmic values, 250. 377 is interesting because it happens to be like, I think that frequency was related to like, free space resistance, and so it's a good reference point. So it's used for RF microwave R cards and absorbers. And then we have this really high resistance material that's only available through, you can see a lot of there's overlap, where it says TCR and Ohmega apply. They can be supplied by either product, but some of them are only supplied, like the very low ohmic value is supplied by only Ohmega apply, and the very high is only applied by the Ticer TCR because of the process. And what's nice is that we've worked with the laminate suppliers, so we basically can take the standard copper foils, and we have different profiles. We could use everything from a relatively rough profile down to some very smooth copper profiles, depending on the need. And the basic copper thicknesses go from 35, 1 ounce, half ounce, 12 micron, and then now we are working on a developmental project where there's a copper that has a 3 to 5 micron copper on a carrier. So what happens is they basically have a copper carrier, and then there's a release layer, and then they plate 3 to 5 microns. Actually, can go lower than that. They go down to 1.5 microns. And then what happens is when you laminate it to your base material, you then peel the carrier off. And people want to do that for semi-additive processing. So if you start with a very thin base of copper, then you can put your photoresist down and plate up, and you can get much finer lines and spaces doing it that way. And so there's some people interested in that, we're developing on working that, putting our resistor layer now on that 3 to 5 micron copper. And we've basically been tested on all the different resin systems out there. So we work with Rogers, Panasonic, Isola, the AGC companies, both Nelco and Taconic, DuPont, so it can be put on flex material. So a number of times it's put on the flex, and it has very good, because these layers are so thin, they have very good flexural resistance. So you can make flex resistors or flex heaters using this material, as well as iTech, Mitsubishi, and others. So there really isn't too many laminate materials we haven't been on. So work very well with all of them. And we supply the product 2 different ways. We can actually sell you we have several, especially in Asia, they'll buy the raw foil and they'll laminate it themselves to their substrate. Whereas here in the US and sometimes in Europe, you'll actually buy it on the actual substrate already laminated to the material. But we could do it either way. We can work with you on that. So the whole concept of ohms per square, what is it, okay? And it turns out that in order to get the resistance value that you want, it's a geometry factor. So when we say ohms per square, if you look at the 3 different sizes, they're all 25 ohms because they're a perfect square. They're a 1 by 1. So whether it's 1 millimeter by 1 millimeter or 1 meter by 1 meter, it's still 25 ohm resistor because the way that this works. The difference in the sizes, though, is how much power you can put to it. So the bigger the resistor, the more power it can take, and also better heat dissipation. So So that's kind of the idea. So when we say that, so when we tell people ohms per square, say ohms per square what? No, it's just ohms per square, okay? And so what you do is you control the geometries to get the resistance value you want. So if you want to go, as an example down here, if you want to go to 50 ohms with a 25 ohm per square material, you just make it a 1x2, so basically 2 blocks. So it's all about the ratio of length to width. So here's an example, and by doing that, you can use different type of patterns. You can use just a regular block, or let's say you want to have a real high ohmic value. You can use a serpentine pattern. So you basically can go like this and make a serpentine, and that will now give you a much higher ohmic value. And what's nice about that is, even using a 25 ohm material, you can go anywhere from a 25 ohm resistor all the way up to a 1,000 ohm resistor or more, depending on how you do the geometry. Okay?
Does all this affect heat dissipation as far as like the serpentine or the thinner, the thicker?
Yes. Yeah. So in other words, what you try to do is you try to design it so that you have to put the power requirement, and you probably want to use, from the overall value, you want to use depends how much space you have also. So we have design guidelines. We haven't actually have so if you contact us, right, we'll go ahead and we'll say, okay, how much space do you have? What's your power requirements? We can help you lay out the actual, what would be the best, do you use a 25 ohm, 100 ohm, it all depends on what you're trying to do. But yeah, heat is something you have to worry about, because this material can be used, one of again, it's a resistor, it can also be a heater. If you put enough power to it, it'll heat up. If you put too much power, it's a fuse. So it all depends on what you're trying to accomplish.
Yeah, 2 questions.
Yes.
So will that material go on the top layer, or you can have it into inner layer?
It's internal. It can go on the top and internal. We have applications where people are using it on the surface, and we have applications where people are burying it inside. In fact, there's some people who use multiple layers. So let's say you have a certain range of resistors. You may turn out that you want 25 ohm material on one layer, and you might want 100 ohm on another layer, just so you can make different resistor values.
Yeah, but because you mentioned that the value depends on how is the profile of the thickness of that.
Yes.
So when we have it in the inner layer,
yes,
so it creates some sort of wavy on either of the copper, and then it changes, the performance, like the impedance. This is one question, and the other one is about the temperature coefficient.
Yeah, I'll go into that. Yeah, one of the nice things about this, the temperature coefficient of resistance is very stable. It doesn't vary, over normal operating temperatures, it doesn't vary that much, and that's one of the nice things about it. Okay, and again, what also happens is that we test the material, we manufacture it, we actually laminate it to a FR4 board, and then we go ahead and we etch resistors, and we measure them. So that's a process control we do every so often. We do it at the beginning of the run and then every so often. And then, but what happens is we know there's an offset, depending on which resin system it's going to go to. So let's say if it's going to, for most of the standard materials, the temperature range of lamination is like maybe 390F to, it's not that high, But if you start going to PTFE, that gets a lot higher. So we find out on Teflon there's a bigger shift. So you can offset for that. So we know exactly, so that's, so a 25 ohm resistor might become a 28 ohm resistor material, but then you compensate for that. And we know that offset. And so the process of making this, it's really a double photographic process, because you start off and you do your typical normal photoresist process. So you go ahead, you put your photoresist down, and now you're going to define both the copper trace and the resistor are going to be formed, okay, initially, okay? And then you go ahead and then you etch off the copper, and then for the Ohmega material, you have to go through a secondary etch to get rid of the resistive layer where you don't want it. And that's usually a copper sulfate. So some people set up a separate bath just to get rid of that resistive material. With the nichrome that comes from Ticer, it's thin enough that typically Cooper etch will go, your standard Cooper etch process will remove it. Okay, that's one of the benefits of the Ticer over the Ohmega, okay? Because it is much thinner and it's easier to get rid of, okay? But then you go through and do a secondary imaging process where now you want to get rid of the copper where you want the resistor layer to be. So you go ahead, you put, you laminate it again, do the photoresist process, but this time you do an alkaline etch, because the alkaline etch will remove the copper, but it won't affect the resistor layer. Okay, so the first step is a cupric etch, the second one's an alkaline etch, which everyone has cupric and alkaline because that's your outer layer etch, and it is typically alkaline. So then you go ahead and then you strip the resist, and now you have your resistors defined. And why do people, there's several reasons for using the technology, and I just want to make sure I'm good on time.
You're
Okay.
good on time.
So, too fast or too slow? It just.
No, you got another 25 minutes.
Okay, that's fine.
Slow
So
down.
I'll leave a little time for
You
questions.
want to move the mic a little bit?
Was that?
Move the mic over toward you a little bit?
You hear better now?
Yeah.
Okay, good. I actually talk loud, so I didn't know the mic. Okay.
Yeah, we got people in the back row.
Yeah. Okay. So, why do people use the, use the technology? And, part of it is, getting rid of surface mounts. That's an obvious thing. Because if you look at, here's an example where you can take all these surface mount resistors, and now you can go ahead and put them inside. And so it really gives you a lot of space that you could use for other things. So you can either keep the board the same size and just put more stuff on it, or you can go ahead and actually reduce the size of the actual board. And so even though this resistive material is more expensive, then we're never going to be on a cost comparison. If you add up all the resistors we replace, resistors aren't that expensive. Okay, so it's not really a matter of the resistor value; it's more of the real estate of the PCB that's actually more valuable. And so, and then of course with the electrical performance, which I'll get to in a second. So, what are the typical markets? I mentioned the iPhone earlier, but smartphones, consumer electronics, and wearables. Right now, most of the microphones, almost probably 90% plus of microphones that go into any device, be it a iPhone or any of the speakers that are out there, the smart speakers, they're using MEMS devices now. So the ceramic part, which is the MEMS device, sits on a PCB, and that gets all getting packaged. Okay, and they need to have an RC filter circuit in there, and instead of having little discretes that take up space and have to be soldered, they're now using embedded capacitors and resistors in order to do that. So it really makes it much more efficient package, makes it smaller, and there's also optical sensors and other things that are in consumables and wearables. So that's a growing market, for this type of technology. And what's nice about it is those things are so tiny that the actual amount of material that's used is very small. So even though on a square foot basis it can get relatively expensive, by the time it gets down to the individual component, it's actually very cost effective. Okay, and then you have you have those type of applications, things like sensors, IoT, all that stuff where miniaturization is important. Then you also have aerospace and defense. A lot of them are really involved with high performance and reliability. Let's face it, any surface mount device you don't have to mount reduces the reliability issue. You get rid of solder joints, you get rid of vias, and so it's a much better application. It's also, by nature, it's also hardened against radiation by doing it that way. So, radar, it's used in, our cards, I'll get into a little bit in a second, and electromagnetic absorbers, trim modules, so aerospace-based heaters. When you put things up in space, lots of times we're worried about here on Earth about things getting too hot. Well, of course, when you're up in space, you worry about things getting too cold. So certain electronic components that have to be at a certain temperature. So up in space, you can actually now put a spot heater directly under the component in the circuit board. We can put a heater right under it where it needs to be critically controlled. Any control circuits, again, commercial electronics, microwave and RF circuits, IC cards, and test boards. The burn-in boards and test boards, they're getting, as things get denser, those boards get more difficult to build and there's less real estate. So if you can embed the resistors, that helps a lot. And again, heaters for also burn-in boards, you can use localized heating circuits, as I mentioned. And again, automotive and industrial sensors. We're working on a project right now where people are looking at having, right now when most people know when it's time to replace their brakes when they hear the squealing, right? And so, we're working on a sensor now that would actually give you feedback on when it's time to replace your, it kind of gives you a lifetime and tells you when you need to, proactively change your brakes. And then also radar components and like that. So, as I was getting into the automatic, controls for cars, there's more need for sensors. And again, sensors is a very good application for this technology. And again, aerospace and defense, we got, millimeter wave radar, both ground, air, and sea, arc cards, absorbers, and then again, commercial growing. Biomedical is a big area that's growing too, where people want to have, sensors, and they need to miniaturize or they need heaters, and so we're seeing that. And as frequencies get higher, all the parasitics and all the problems of these passive components becomes more critical. So now, even though this technology has been around for quite a while, it's almost like the necessity of it is growing as we're going into higher frequencies.
Excuse me.
Yeah.
I may miss one point.
Yeah.
Did you say that you monitor the value as the resistance ages?
Yes, we have experience. We've done aging stuff.
I mean,
Yes.
for example, do you mind to just deliberate on that?
I have a little bit on that. Okay. So here's an example of what we, one of the bigger examples right now is these MEMS modules. So you can see that, there's 336 little PCBs in the 3.5 by 2.5 inch area, and so and you could see kind of like the exploded version of the device. And so there's a little circuit board. If you look down here, that's a circuit board. Then it sets, there's the actual MEMS device. There's the IC. And then you just put the seal on it and you're done. So it makes the manufacturing of these much easier. And what's nice is that because of the number of, billions of MEMS mics are made a year. Now again, it doesn't take up a lot of material to make that many mics, but it's still, there's a lot of experience now, especially in the commercial shops in Asia, using this type of technology. So if somebody has a high volume application, right now I have a biomedical device company that's looking at changing from a ceramic-based circuit board using thick film resistors to a FR4-based board using thin film resistors, and they expect to cut their cost in half for their sensors by going that way. So even though our material is more expensive than traditional PCB materials, it's still a cost savings when you're going from a ceramic base to a PCB base. So we see that as a growing area. And then other applications are like these. A lot of RF microwave stuff. You can see, I am not an RF microwave engineer, and I'm still learning about that stuff. But you can see things like power dividers, where there's little, it's hard to see, but these little, when you get the presentation, you'll see a little bit better, but these little gray areas are the little resistors that sit between that. So you can make a very efficient power divider without having to use any surface mount devices. So you can embed your power divider into your board. And then also for arrays, again, we have these absorbing materials and things, so it makes a very efficient, antenna array. And again, the big thing is, we want to get rid of solder joints, we want to get rid of the vias, because they all put in, every time you make a connection, you lose performance. And so by going from the copper trace directly to the resistor, and that's your only connection, you're going from the copper to the resistor, you don't have all that vias and all the solder and all that stuff to deal with. You get rid of the parasitic inductance and capacitance. So we've had people use this technology and say this is the best, for high frequency, it's the best resistor technology. They can't find anything on the market. Even the best discrete resistors can't compete with this overall performance-wise. And again, on people looking at it for interposer cards, again, this is a place where space is very valuable. And so you can see here we have like termination resistors. What's nice is you can put the termination resistor right in the trace. So there's no extra, extra work basically they have to do. And so you can, and usually the most expensive real estate is around the IC because everything gets crowded and it's getting into there. So if you can get rid of vias and things of that type, you got more real estate. It makes it easier to do your routing around your ICs. And if you look at the SI improvement, you can see the eye diagram. You get much less noise and you get much cleaner signals, especially at higher frequencies. So again, it's sometimes not driven just by cost or miniaturization. It's driven by performance because for some very high level systems, you can't deal with with a lot of noise. And you can put your resistor elements. Right now when you put your resistive element, you're kind of given by the amount of area you have on the surface, and everything's competing for that surface area. You've got capacitors, you have ICs, you have all the stuff that's going on the surface. Now you can put your resistors down inside the board. It takes a lot of that pressure off, and so it ultimately can be much easier to design with this type of technology. And another application, and we're still finding new applications. Again, it's a technology that's been around a while, but we're still finding people that are finding interesting ways of using this material, like radar, absorbing materials, R cards or resistive cards. It can be a high impedance surface. So when people are looking at trying to clean up their signals, and get better signal to noise ratio, it really benefits to have this type of material available. So you can basically take our material and then you can form different patterns on it to get different type of antenna performance. And here's an example of comparing the inductive reactance of our material versus just the best available surface mount. You can see quite a bit of a drop. And as frequencies goes up, like we all know, as frequencies goes up, the difference gets even bigger. It gets much better, at the higher frequencies. And so that's what a lot of people are interested in this type of material. And so if you look at our resistor roadmap, the basic things are, the sheet resistance, we think we've got everything covered that we want to do. No, we don't see coming up with new resistor sheet values, okay? Between 10 and 1,000 ohms per square should cover, 99% of the resistor values that are needed. But we are looking at, what are the copper foils? Like I mentioned, we're working on this 3 to 5 micron copper, which we think is going to be very good for like chip packaging or other places where people will have really fine lines and spaces they want to accomplish. And so we hope to have that, actually we're in the process of getting some samples prepared, for sampling. So if anyone was interested in that material, we should have some, within the next 3 to 4 months, we should have some for testing. And then of course 12 micron is available. I'd say right now the largest on basis of sales, 18 micron seems to be a very common, because a lot of signals are 18 micron. And so using it on signal layers, so 18 microns is probably the most common, but we do 1 ounce. We haven't really seen any demand for 2 ounce. Not that we couldn't do it. It's just that we can code on any copper. It's just a matter of what the needs are of the customer. Yes.
Can you do carbon fiber cores?
Do we?
Yeah. Have you?
I have to check on that, to be honest with you.
Well, our military wants that stiffness that you got with carbon fiber.
So we put our material on carbon fiber.
Yeah.
Yeah, we just have to look at what the bonding, the adhesion. There's no reason we couldn't. Let me put it that way. Have we done it? I can check. But could we do it? Anything's possible. We just have to make sure we get a good adhesive layer. Yes. Right.
John, when you have a layer of resistors
Yep.
that are going to be embedded in a multi-layer,
Yes.
That particular layer of surface, is it dedicated only to resistors, or are there other functions?
Oh no, it basically it's just like your signal trace. It's just your signal. So it doesn't really, you don't have to get rid of.
So the nichrome that's underneath the other technology on that layer, it doesn't interfere with
No.
performance, speed?
Yeah. What's nice is, as opposed to pure nickel, nickel phos and nickel chrome aren't magnetic. So you don't have that loss concern, that you would have with having a nickel layer down there, just a pure nickel layer.
And all the oxide treatments, there's no attack or lateral
Nope.
issue?
Yeah, the biggest thing is making sure you remove all the resistor material so you don't have any long-term reliability problems, but most people do that, that's not an issue.
Any constraints on having resistor coil on 2 sides of the core?
Nope. Most people put it on one because that's what they need, but there's no reason they couldn't do it on both sides, And in fact, I don't know if I can't remember if it's in the presentation here, but we can actually, put it on capacitor material. So we could take our material and put it on 1 mil or 2 mil, like the VC or the Farad Flex or the Intera product. So we can combine a resistor capacitor material if necessary. In fact, we actually did a joint paper when I was back at Open Mitsui with Ohmega, and it turned out by having that ground plane on the other side actually helps with heat dissipation. So you actually can drive the power up. So one of the things when you're designing is that you'd like to have a copper sink as close to the resistor as possible, if you have a power concern. Again, most of the time you don't need it, but if you're going to be driving the power up, you have a close copper sink, that'll help with dissipating, the heat that might be generated. So yes, you have a lot of design flexibility, with the material. Because like I say, you're not getting rid of the routing, because actually let's face it, most signal routings will have a via that goes up to resistor. So you're just kind of getting rid of that whole via and all the inductance and everything that's involved with it. So the two things that are driving us right now, there's actually 3 things. It's copper thickness, getting that thinner for the semi-additive process. The copper foil profile, we're working with our main supplier and others on trying to get the copper profile down, because people want it for high frequency. And so, which also means we have to work with the material suppliers on getting a good adhesion. So that's always the issue is, we can basically coat this on dead smooth foil. Okay, we could coat it on rolled annealed if we wanted to. The thing is, will it stick to anything? So that's what we have to work on is, adhesion promoters and then working with the laminate suppliers to make sure we get at least, most people want at least 4-pound peels. So that's what we kind of go for. Sometimes people will live with 3.5, but that's what we're trying to work on. And again, so if somebody has a particular need of a material, we could work with their supplier. Like you mentioned, the carbon fiber, we could work to see what we can accomplish. And before I get into reliability, I just want to talk about how, the design is right. So there's different, obviously there's multiple CAD software programs out there and they all handle it a little bit differently. But basically what, unfortunately, I don't think, unless you want to correct me, Scott, is that I don't know if there's a real, no one has a suite that basically you say, that will automatically design a resistor for you. I think most of them will give, what you basically have to do is you have to create your trace layer, and then you leave your opening and your resistor is going to go, and then you use us to help you design the resistive element for that space you have, and then you create that as a separate layer. Okay, because you're going to need the two artworks anyway. You're going to need the artwork for etching the traces, and you're going to need that separate artwork for etching, for defining the resistor layers. So it's not really hard to do, it's just that it takes that extra step. So you're basically almost creating an individual resistor element, like you would be doing, you create an element just like you would have a discrete. You basically do the same thing. So you create a library of resistor elements, and you can reuse the elements over and over again.
Sorry, so imagine we are done with our PCB design. Do we have to get you to just insert those resistors, and or we can get something from
no,
you?
we have a spreadsheet we can give you. Well, it's actually a program they could use for give you guidance. So if you say, I need this type of ohm resistors, this space I have, this is the power. It'll give you, it'll tell you kind of how to lay out there. So you don't have to call us every time. We have a tool that can help you. And after a while, you get used to how you do it and stuff, and then you just go ahead and take that element and put it into that layer.
Okay, thank you.
How about if you want to change the value of the resistance?
What's that now?
How about if we want to change the value of the resistance? For example, rework purposes. Yes, so.
Like laser trimming?
Yeah. So in other words, in fact, there's a number of people that either for tolerancing or for tuning, they want a certain value. So you can go through with a laser and actually, create a pattern to basically, raise their. So you'd over design, you make it so that's less resistive. You make a resistor so it's less, and then you would trim it to get into the resistive value that you want. But you can also, again, you can control also. If you let's say you designed a 50 ohm resistor, now you need a 25 ohm, just go back into the software and then you say, okay, this is the size I need. Or we could change the base resistor value of the material. So you could use the same footprint and you can go from, let's say you want to double the resistance, you go from a 25 ohm per square material up to a 50 ohm. So again, if you want to do trimming to get exactly what you want, you can do that on the material. And people do that all the time.
Excuse me, can we do trimming in order to make sure, we have like the partial values. For instance, I want a 9.31 kilo ohm.
Yeah.
Can I do that?
You can trim to almost any. What's nice about these things is you can trim to almost any value you want. You're not unlike discretes where you buy in increments.
Yeah. Okay.
You could, if you want a 43 ohm resistor, you can make a 43 ohm resistor.
But how about 43.33?
Oh yeah, you can do it. The thing is, because we're still, we have a tolerance on the material about plus or minus 5%. Okay.
5%.
Yeah, but then the board shops have a tolerance of about plus or 5. Depending on the size of the resistor, they have a tolerance. Okay, and so, but for many applications, it turns out the tolerance, just because you can buy plus or minus 1%, still means you always need plus or minus 1%. Okay, so anyway, but you can then trim in to get the tolerance that you need. In fact, the biomedical application I was talking about earlier, they put the resistive material on the surface and they trim themselves because they have to do it as part of the overall system. So they actually use the trim to kind of tune the whole circuit, and they do that themselves. So laser trimming is a very common, and this material is so thin it doesn't take very much energy to basically do it. And then people have done all sorts of studies on what type of cut. do an L cut, you do a, and so there's lots of different, ways you can do that to get, because it all depends on how the current is flowing,
So you're doing, if you're doing trimming, and this is on the internal layer,
Yeah.
the fabricators that you work with, do they have laser trimming equipment, or do they?
It depends on the fabricator. A lot of them, because they have, since most people don't need trimming, a lot of them don't necessarily. I know that there was a company working on taking their standard laser drills and trying to use them as trimmers. That's a little bit tricky, But again, if you need to, you can do it. It's just that it's not really a common practice, but it can be done. Okay, so you have to talk to your board shops about that. But again, most people can live with the tolerances that we provide. And again, one of the things about the semi-additive process, let's say with that thin, is it can get much tighter. That with laser direct imaging, you can get much tighter tolerances on the imaging process, so that will help as well. And the tolerance also depends on the size. So the bigger you can make the resistor, tolerance-wise, is going to be better. When you make little tiny resistors, obviously any imaging is going to be an issue. But also, too, is when you're laying it out, you got to make sure you got the right amount of overlap. You have to adjust for misregistration. So you have to make sure you design properly to give a little bit of extra room so you can make that make that connection.
But again, with direct laser imaging, you've got better control of that anyway.
Yes. So we've done all your typical, aging type of studies, and we've done, the humidity testing at 40 degrees and 93%. It's pretty much not, doesn't really, bother it. You have very small changes after both 21 days and 56 days. Again, it all depends. If it's embedded inside the board, you're going to have better performance if it's on the surface, but it's going to be covered typically with solder masks. If you have a good solder mask, it's not going to be an issue. So again, you don't see very much change. In fact, thick film usually changes a bit more than our material does. Thermal cycling, again, we've seen very little percentage change with thermal cycling, going from 125 to 25 degrees C, and you get very very little shift in the ohmic values. And then you do both biased, and we've done some unbiased and biased aging. And again, after 100 hours, you can see we got very little shift in the. And this is all verified. This is not by us. This is by Alcatel did a lot of the initial testing on this stuff. And then solder floats. Again, what's nice about it, because it basically is as stable as the material it's on. So as long as the material holds up to all the testing, we don't see really much change, in the product. And again, we've done other studies, stabilization bakes, and again, no problem with that. Temperature cycling. And then, again, we've gone through a lot of different, especially since we have space applications, people have gone through all sorts of aging tests and the temperature cycling, and we've not seen any real problems, with the material. Again, the tolerance I told you, usually etch tolerance about, 5%. The minimum resistor width we recommend is about, 200 microns, so that's about, I'm trying to think, 8 mils or something like that. There's a certain practical limit to how small you want to make these things. But again, we've done really high frequency testing, and it makes very little, the Ohmega ply or the Tyser doesn't really seem to affect the overall performance at those very high frequencies of the actual signal trace. Again, more thermal cycling, both microstrip and strip line, and not seeing any problems. And so you mentioned the temperature coefficient of resistance by both microstrip and strip line is less than plus or minus 2% shift over the range of 155 to 125. So again, it's pretty stable material. You don't see much of a change over the typical temperature ranges you're going to see. Again, we can put milliwatts. Everything's typically going to be milliwatts. You're not going to be driving a lot of power through these things. But then again, most circuits don't require all that much power for doing these type of resistors. And again, we did 2-point power divider environmental test, and saw negligible shift in anything over these over 500 cycles of cycling, high temperature storage, and humidity without any real problems. The only thing that again, and we've also done the human body ESD testing, because one of the things you're worried about is it is a discrete component in a way. So we have to make sure that even though these things are thin, we've done the zapping of it to see if it holds up, and except for maybe the really thin stuff like the 1000 ohm, it all handles the human body model for ESD pretty well. And then we've done HATS testing, at lead-free assembly conditions, and again, thousands of cycles, 10.85 minutes per cycle, and again, very small change in the, and we had 15 coupons per resistor network, and you get a very small change in resistor values. It's very stable. These are just some, these are things from our customers. We work a lot with Rogers. They've gone through the bend test. And again, I don't know, it depending on how many cycles you plan on going through, it's not designed for dynamic flex, so not something that's going to do 10 or 20,000, 30,000 cycles. It's definitely good for flex to install. And it also has the resistance changed, even after 1,500 cycles, it only changed 6%. So it all depends on the bend angle and the frequency of bending, but it does hold up pretty well, because these things are very thin. So, it bends, it doesn't really crack, it's a pretty stable type of operation. And then, Delco did a number of different tests on it and found it to be very, very stable. So really haven't had any complaints on the actual performance or reliability of the material. So the thing I want to leave you with is that it's a very mature technology, but it's still in a lot of ways in its infancy of implementation. And we're seeing now that the industry is catching up to the point where it needs this type of technology. So those who can implement it, I think, are going to see the value. It's not going to replace all resistors. There's the places where it seems to shine is when you're making something where miniaturization is critical, like the MEMS microphones, where you can get a lot of resistors per square area, so you maximize the use of the material, but also for high performance. And we're seeing, again, people are making some really unique RF microwave configurations with our material as the absorber layer, and then they got the antenna structures. And so we're seeing a lot of growth in that type of area as well. We continue to invest, with having this new parent company of Quantic, with the resources of Arcline behind it. Now we're putting more money into R&D, improving our facilities. Again, we have, where right now our main facility is right here in Culver City, where the Ohmega is. The Tyser product is actually made in Connecticut, but the finishing is done in Phoenix and in Chandler, Arizona. So we're a US-based company, but we ship all over the world. We have a very good relationship in Asia with a number of the major board shops there as well, especially for the consumer side. And so we partner with leading OEMs to understand the market trends and what their needs are, and we're trying to make sure we're keeping up with the needs of the industry. And again, it's a proven technology built on a long, standing foundation, and we work well with both the material suppliers and your board shops, to get you what you need. So with that, I appreciate your time, and I'll answer, any questions.
Wait, take Ken first.
Okay.
Yeah.
I have an application where I have like a 5 gigabits per second LVDS circuit, and it's going into an FPGA.
Yeah.
As far as putting the termination 100 ohm resistor between the pads, is that feasible on like an 810 millimeter pitch pad?
Yeah, I have to take a look at it. We try to, we want the resistor to be a little bit away from, like, there's a certain distance we like to have away from the actual pad itself. It could be put between it, because when you're drilling, you generate heat, and we don't want to cause, any real concern with that, with the resistor there. But yeah, you can put resistor right between.
It's an FPGA pad, so it's on the surface.
Yeah.
So that resistor, the idea is put the resistor right between the pads.
You could put it right there.
There's no drilling.
Yeah, you could do that. That's not a problem.
It'll fit in the 0.8 millimeter pitch, 100 ohm.
Put it this way: if you can define it as far as etching, you can put it there.
Do you have like samples we can order, because I'd love to?
Yeah, I have some samples I can.
Okay.
I can send you samples, but I also have like a little over
Yeah,
at
I'd
the
like
desk
to
there. I've
get
got some.
one, because I like to do the potential divider. It's we
Yes.
have it at a critical place, and I like to test that. And the last question is about how long this technology has been in use.
How long has this technology been in use? Since the 1970s.
Oh.
In fact, Cray Research, remember Cray, Cray supercomputer? They were one of the first users of it, and they were actually using it in their supercomputers as a termination resistors. So it goes back quite a ways. So it's not a new. I mean, actually they've been making this product since the late 70s in regular. So it's again.
It's the first time that we are learning it from you. I mean, I'm learning it from you.
Well, that's part of my mission is to go out there and to educate people. And hey, we've been here,
I think that kind of to kind of wrap it up, we've learned a lot here, but in terms of implementing it, what is the easiest way for people that are new to this? I mean, obviously, they gotta have a fabricator that can support it.
Yes.
But from a design perspective, to get their hands held, what does Quantic do to help people make this transition?
Well, first you contact us
Yep.
and give us an idea of the design. Then we can recommend the right material. And then if you have board shops on your QPL, we work with a number of board shops. In fact, a lot of the shops are here in the U.S. as well as overseas has processed the material. So you would come to us and say, this is the board shop I'd like to work with. And then we'd work on getting samples and getting that taken care of. So, so we could help with that. Yeah, like example, we have the customer, we're making a sample right now where the customer that does the laser trimming, they want a sample on an FR4 laminate with all the copper removed. So they can do laser trimming experiments, just to make sure they can trim it to what they need. And so we're preparing samples right now. So if people need samples, we can do that, as well as work with whatever board shop they'd like to work with. And if their principal board shop doesn't use the technology, we could recommend somebody that does, or we could work with that board shop in order to implement it.
The path to success is to work with you guys to help the designers learn how to do it, who to work with so that they can make product.
And again, we have people like Panasonic with here, and so we work with the laminators. So they'd say, what type of material do you want on? And then we work to make sure we use the right copper foil with the right laminate to get the characteristics that we need.
All right, John, thank you.